How many numbers would it take to describe the moon? To start, it's covered in countless craters from billions of years of asteroid impacts. An exomoon orbiting a distant exo-Earth might look similar at a glance, but its pattern of impacts would be entirely different. To describe each crater accurately, you'd need at least two coordinates, longitude and latitude, for every single one plus each crater's size. Very quickly, you'd need thousands of numbers just for the craters, before even considering the moon's chemical makeup and how it varies across the surface. The numbers needed would soar from thousands to millions and beyond. And that's just for a moon, one of the simpler objects in the cosmos. How many more numbers would be required to describe a planet, a star, a nebula? Or how many numbers would it take to describe the most massive single objects in the universe, black holes? The answer for these cosmic monsters might surprise you. 3. Only 3 numbers. No matter their immense weight, no matter where they formed, whether in our Milky Way or a billion light-years away, just 3 numbers are enough to define them completely. This makes black holes seem deceptively simple. Only 3 parameters classify them: mass, electric charge, and angular momentum. Know these 3 and you know everything. Yet there are countless ways a black hole can form. They can grow slowly by swallowing dust and gas over eons. They can be born from the violent collapse of a massive star in a supernova. Some might grow through repeated mergers with other black holes. We can even imagine a hypothetical black hole formed from every encyclopedia, every data bank, every piece of information, and every number ever conceived by any civilization in the cosmos. Anything and everything in the universe could fall into a black hole, yet once it forms, all that vast information is reduced to just 3 numbers. How it was made and what went into it becomes almost irrelevant. So the question arises, given the nearly infinite possibilities for creating a black hole, how can they be described by only 3 numbers? Where does all the other information go? Has the black hole forgotten its origins, or does this information survive in some hidden form? What truly lies inside a black hole, and what could that mean for the rest of the universe? Where do we really come from 8 billion years ago? It's a fascinating journey to trace our origins. In the 1780s, the life of a country priest in the Church of England was not especially demanding. It offered a large house, a decent income, servants to handle chores, and younger curates to conduct services and visit the sick. For those who wished it, a life of leisurely comfort was available. But for those who sought more, there was ample time to ponder the world deeply. This is how the English parson John Michell spent his days. By the 1780s, Michell had a solid grasp of how gravity worked. A century earlier, Isaac Newton's theory of universal gravitation had revolutionized science. Newton argued that gravity was a universal force. Anything with mass exerted a gravitational pull, instantly affecting everything else. Nothing could escape gravity's force, not even Michell considered light itself. Newton had also proposed that light consisted of tiny particles, little atoms of light we now call photons. If this particle theory of light were true and gravity was universal, then gravity should act on these particles of light, tugging and pulling them back. Michell also knew light traveled incredibly fast. Earlier in the 18th century, astronomer James Bradley had measured the speed of light accurately by studying the aberration of light from distant stars. As Earth moves in its orbit, the combined velocities of Earth and light cause a slight shift in the apparent position of stars. Through this, the speed of light was known to be about 180,000 miles per second. This was fast, but not infinite. Michell also understood intuitively that an object thrown upward will fall back down. But if thrown upward fast enough, it can escape Earth's gravity entirely. This threshold speed is known as escape velocity, the minimum speed needed to break free from a planet's gravitational pull. Using Newton's laws, it's straightforward to calculate this escape velocity for any planet based on its size and density. The more massive and dense the object, the greater its escape velocity. 4 kilometers per second. 2 kilometers per second. For Jupiter just under 60 kilometers per second, and for our Sun about 617 kilometers per second. But Michell imagined an even denser body. What if a body were so dense that its escape velocity exceeded the speed of light? For such an object, light emitted from its surface could not escape. This body would appear gravitationally massive yet completely dark, trapping even light within its grip. While Michell's reasoning used Newtonian physics, later superseded by Einstein's theories, the concept he described is clearly recognizable today. His work, though the term wouldn't be used for almost 2 centuries, was the first description of what we now call a black hole. Michell was far ahead of his time, and his idea seemed a mere abstract curiosity. It was shelved for about 150 years. The next time this concept would be revisited was in the grim trenches of World War I, where German astronomer Karl Schwarzschild, seeking an escape from the surrounding horror, pondered the equations of Einstein's newly published theory of general relativity. Einstein had developed his special theory of relativity in 1905. A decade later, he succeeded in extending it to include gravity, creating his general theory of relativity. This theory required 10 complex equations to describe it. When first written, they appeared daunting and nearly impossible to solve. In 1915, the methods to solve them were unknown. Schwarzschild sought the simplest possible solution he could imagine: a spherically symmetric spacetime around a concentrated point-like mass. After careful calculation, he found a solution now known as the Schwarzschild solution, arguably the most famous solution to Einstein's equations. Schwarzschild's solution involved one parameter: a uniform spherical mass. In general relativity, mass warps the nearby spacetime. The degree of this deformation depends on the distance from the mass. The closer you are, the greater the deformation, while far away, spacetime is nearly flat. The Schwarzschild solution revealed a profound and striking property. As you approach the mass from infinity, there is a critical distance where something strange occurs. Some terms in the solution appear to approach zero, while others tend toward infinity. What did this mean? Without delving into the full math, these zeros and infinities at a critical radius, known as the Schwarzschild radius, indicated the presence of an event horizon for the black hole solution. A spherical shell at a specific distance from the black hole center representing a point of no return. Nothing can travel faster than light. Outside the horizon, an object moving at light speed away from the black hole can escape its gravitational pull and reach infinity. But any closer than the event horizon, escape becomes impossible, even for light. The laws of physics themselves forbid it. Any astronaut crossing the black hole's event horizon finds themselves on a one-way trip toward the center. Inside the horizon, time always points inward toward the singularity. As the astronaut falls deeper, gravity's pull grows stronger and stronger until they reach the singularity itself, a point where the laws of classical general relativity break down and spacetime curvature becomes formally infinite. This echoed Michell's calculation of a radius where escape velocity exceeds light speed. If a mass is condensed within its Schwarzschild radius, it collapses inescapably. The Schwarzschild radius for our Sun is about 3 kilometers. For Earth, it's less than a centimeter. A human's Schwarzschild radius is on the order of 10 to the power of -23 meters, smaller than an atomic nucleus. 2 light-years, a truly colossal black hole would eventually form. Schwarzschild's solution was found in 1915, but like Michell's work, it was seen as a mere intellectual curiosity for half a century. Did it represent something physical, or was it just a mathematical artifact? Unfortunately, as quantum mechanics revolutionized physics through the 1920s, 1930s, and 1940s, gravity and general relativity were largely sidelined. The American physicist Richard Feynman's comments on a gravity conference in the early 1960s capture the sentiment of the time. However, this stagnant state changed dramatically in the late 1960s, as theoretical and observational breakthroughs brought black hole research and general relativity roaring back to life, both in theory and observation, a trend that continues today. In the public mind, one scientist is more associated with this renaissance than any other. Among the icons of 20th century physics, Stephen Hawking holds a special place. His remarkable life story has inspired millions. Born in 1942, He studied undergraduate physics at Oxford before moving to Cambridge for his PhD. But during his doctorate, Hawking's life changed drastically in two connected ways. First, at age 21, he was diagnosed with motor neuron disease, a degenerative muscle-wasting condition with a typical life expectancy of about 18 months from diagnosis. Second, having coasted to a first-class degree at Oxford, he began working with intense focus for the first time. Faced with the prospect of an early death, he threw himself into his work, driven by a desire to achieve something and leave a legacy. Hawking would far outlive expectations, eventually passing away in 2018 at age 76 as one of the world's most celebrated scientists. His scientific fame stemmed largely from the first black hole renaissance, occurring roughly between 1967 and 1974, during which an extraordinary period of collaborative creativity between Hawking and mathematician Roger Penrose revitalized the stale field of general relativity. Together, Hawking and Penrose proved a set of key theorems. If you start with a group of heavy particles close together, pulling on each other under gravity, it's not intuitively clear what will happen. They might collapse into a black hole, or they might slingshot away from each other. Hawking and Penrose resolved this. They showed that under general conditions, collections of matter under gravity would collapse, and the inescapable endpoint of that collapse would be a singularity in spacetime, surrounded by a black hole. This was not mere intuition or expectation, it was a rigorous proof. Their collaboration also changed how relativists viewed space and time through a novel conceptual tool called Penrose diagrams. These diagrams simplified much of the complexity of solutions to Einstein's equations. Suddenly, it was possible to have a clear, global view of causal relationships around black holes, a diagram showing which points in spacetime could affect which others. In these diagrams, light always travels at 45-degree angles, making it easy to see causal connections. The horizon could be viewed as the boundary beyond which there can be no causal contact with space infinitely far away. As his body weakened, Hawking's mind soared across space and time. There was good reason to think that the bizarre objects described by these equations, black holes, could truly exist in our galaxy. Fortuitously, at the same time, astronomical telescope technology was advancing rapidly. As satellites launched telescopes into space, for the first time the sky could be observed above the clouds, not just in optical light but also in other wavelengths like X-rays. This led to a shocking discovery. The X-ray sky was far busier and more crowded than expected. One source, Cygnus X-1, was especially bright and compact. Where did these energetic X-rays come from? How could they arise from such a small region? The only plausible explanation was a compact black hole, with the X-rays emitted as matter accelerated into it. Since Cygnus X-1 was identified as a black hole in the 1970s, many more have been discovered. There may be as many as 100 million black holes in our galaxy alone. In 2015, colliding black holes were first observed directly when the LIGO Observatory in the United States detected gravitational waves from their merger. But the excitement wasn't limited to astrophysical observations. In offices and on blackboards, in equations scribbled during late-night creative bursts, the theoretical exploration of black holes became a bizarre new playground for the most extreme questions in the cosmos. Nothing is more familiar than the human face. While easy to recognize, faces exhibit almost infinite variety: age, complexion, hair, freckles, smiles, teeth, skin texture. How many numbers would you need to specify a human face completely? A vast amount. Something far less familiar and seemingly more exotic is a black hole, yet in a way they are far simpler. This simplicity was reflected in the solutions to Einstein's equations, though finding them wasn't easy. Soon after Schwarzschild's 1915 discovery of the simplest black hole solution, another generalization was found: an electrically charged black hole, known as the Reissner-Nordstrom solution. It wasn't until nearly 50 years later, in 1963, that the most important generalization appeared: the Kerr solution, named after New Zealand relativist Roy Kerr. Like Schwarzschild's solution, it described an uncharged black hole, but one with angular momentum or spin, a black hole spinning on its axis. Imagine a supermassive ballerina, rapidly spinning, extremely heavy, arms outstretched. This cosmic ballerina is dense enough to be almost at the threshold of forming a black hole. As she brings her arms in to spin faster, she crosses that density threshold and collapses into a black hole. But this is a spinning black hole. The angular momentum she had before collapse doesn't disappear. It goes into the black hole, as reflected in the Kerr solution. But why were there so few black hole solutions? Only Schwarzschild, Kerr, and their charge generalizations. This wasn't due to a lack of effort. As physicists studied general relativity and considered what solutions lead to black holes, they first suspected, then proved something distinctive about these solutions. A result now known as the black hole uniqueness theorem with remarkable implications. Most astronomical objects have nearly infinite individual characteristics. Quasars are vast cosmic engines. The brutal friction and temperatures around their central black holes create a superpowered dynamo. Trillions upon trillions of numbers would be needed to describe even a vaguely similar object. Stars, though seemingly more straightforward, come in endless variety and evolve dramatically over their lifetimes. From supermassive first stars living only millions of years in the early universe, to ultra-low-mass frozen stars expected to linger into the universe's twilight, they represent a bounty of possibilities. Even a simple subkilometer asteroid has its unique features and birthmarks, pocked by millennia of travel through space. But for black holes, this wasn't true. The allowed solutions were tightly constrained, completely characterized by just three properties: mass, electric charge, and angular momentum. That was it. No other parameters existed. Three numbers gave you everything. Every black hole in the universe could be classified by its mass, charge, and spin, nothing more. Behind the mask of the horizon, there are nearly infinite ways a black hole could have formed. So how do all these starting possibilities end up as just three numbers? Let me count the ways. When a physicist hears these words, they immediately think of thermodynamics, the science of heat, temperature, and entropy. Look around. The room you're in is filled with air, a gas at a certain temperature and pressure. We can feel these properties. Hot or cold blasts of air, pressure changes in our ears during a plane's descent. Yet we don't feel the individual atoms making up the gas. Inside the gas filling any room, an almost uncountably large but finite number of molecules bounce around. There are so many that we, as large beings, cannot resolve individual atoms. When we say a conservatory is hot on a summer day, we don't say the gas molecules are moving faster. We simply say it's hot, even if we vaguely know that heat is fundamentally about atoms moving faster and carrying more energy. Gases have temperature and pressure. Black holes have mass, spin, and charge. For both systems, we characterize them with a few numbers. For both, these numbers hide an internal cornucopia of states and possibilities. A quantity called entropy counts the number of internal states a system has. Entropy depends on bulk parameters, like temperature and pressure for a gas. For given values, it counts the number of internal microconfigurations that can produce them. The more microconfigurations consistent with the bulk parameters, the higher the entropy. For a gas, entropy measures the total number of ways the molecules can be moving internally. The vast number of ways the gas's atoms can move given a fixed pressure and temperature. This entropy increases with temperature, which makes intuitive sense once we know gases consist of many tiny molecules. Higher temperatures mean molecules move faster and carry more energy. There are simply more ways to move faster than slower. In the limit of the slowest movement where speeds vanish, a stationary particle has only one way to move, no motion at all. But can these thermodynamic concepts, familiar from gases and rubber bands, really apply to black holes, some of the most mysterious objects in physics? Remarkably, yes. Even though there are no atoms whizzing inside black holes, or stretchy polymers, all thermodynamic concepts still apply. Just as we can talk about the temperature or entropy of a gas, we can talk about them for a black hole. This idea dates to the early 1970s. first suggested by Jakob Bekenstein and later fully developed by Stephen Hawking. Bekenstein was John Wheeler's graduate student. Wheeler, who coined "black holes have no hair," noted in discussion that when you mix hot tea with cold tea, the overall entropy increases in a way that can never be undone. But if the mixed cup then fell into a black hole, all evidence of this mixing would vanish as everything was swallowed into the fixed, unique black hole solution. This got Bekenstein thinking. Could it really be that mixing hot and cold tea increases the universe's entropy, but throwing the tea into a black hole would cause all that entropy to be lost? This seemed impossible. It contradicted the almost sacred second law of thermodynamics, which states that the entropy of the entire universe must increase over time. This law is one of the most cherished in physics. Arthur Eddington, known for his work on relativity and nuclear fusion, once said that the law that entropy always increases holds the supreme position among the laws of nature. If a theory disagrees with Maxwell's equations, so much the worse for Maxwell's equations. If it contradicts observation, well, experimentalists sometimes bungle things. But if your theory is against the second law of thermodynamics, there is no hope. It must collapse in deepest humiliation. So perhaps Bekenstein thought, just as a cup of tea has entropy, and the entropy increases when two are mixed, the same should be true for a black hole. When the tea is thrown in, it should increase the black hole's total entropy by 1 cup of tea's worth. This led Bekenstein to the remarkable conclusion that black holes should indeed have an entropy, now called the Bekenstein-Hawking entropy. It was a truly bizarre discovery. Black holes have entropy, but what did it mean? Which is the hottest black hole in the universe? Since the first discoveries of astrophysical black holes in the 1960s, a whole range have been found. Their masses vary enormously. The heaviest known black holes, like Phoenix A or Ton 618, are around 100 billion times heavier than the Sun. These ultramassive black holes sit at the centers of enormous active galaxies, powering spectacular quasar jets with immense energy. The lightest known black holes, detected as dark orbital companions to stars or pulsars, are only a few times heavier than our Sun. Candidates for the lightest include the orbital companions of PSR J500 and 144002e, or the red giant V723. Bizarrely, these miniature black holes are 1 billion times hotter than the distant supermassive giants that power entire galaxies. Though with a temperature just over 100 millionth of a degree, hotter here is strictly relative. So black hole temperatures are tiny, but not zero. Where does this heat come from? By the early 1970s, Bekenstein and Hawking had determined that black holes should have entropy. Time's arrow, the second law of thermodynamics, continued to point forward. Fire particles at a black hole, and as they fall in, the particle's entropy should transfer to the black hole. The universe's overall entropy would increase, satisfying the laws of physics. Or so it seemed. But as Hawking thought more deeply, his remarkable mind identified a problem with this picture. Imagine hot gas falling into a black hole being completely absorbed. The resulting black hole was thought to be cold, dark, and compact. Nothing could escape. It seemed to be a zero-temperature object. In all other physics, when hot and cold objects mix, the cold object's temperature increases. Yet here, the black hole seemed to remain inert at absolute zero. This was the very idea of a black hole. Not even light could escape. But Hawking introduced a striking and surprising idea. Embracing the notion of black holes as thermodynamic objects with entropy, he proposed that black holes also have a temperature. Not a mathematical analogy, not a gravitational equivalent, but an ordinary temperature with the same meaning as that of ovens, boiling water, or the weather. The most exotic objects in the universe suddenly became eerily familiar. The classical laws of thermodynamics, dating to the 19th century, relate entropy to temperature. Specifically, they state that an object's temperature is the inverse of the rate of change of its entropy with energy. For a gas, injecting extra energy increases the number of gas configurations. By calculating this precisely, we can determine the gas's temperature. For a black hole, the entropy is actually set by the area of its horizon. In the simplest Schwarzschild case, This entropy behaves as the square of the black hole's mass energy. Plugging this into the classical thermodynamic expression for temperature yields a striking result. The black hole must have a temperature, and this temperature changes inversely with its mass energy. Big black holes are cold, small black holes are hot. The temperature of a typical astrophysical black hole in our galaxy, formed from a collapsing star with a mass slightly larger than the Sun, is around 1/1000th of a degree. However, a much smaller and hypothetical black hole formed by compressing something like Mount Everest down to a point would have a temperature of hundreds of billions of degrees, vastly hotter than the centers of the largest stars. This unusual property means black holes behave opposite to our intuition. A normal fire starts hot. As it gives off heat, it cools, eventually fading to ashes and then nothing. Black holes, on the other hand, become hotter as they lose energy. While a black hole starts cold, it gets hotter as it radiates energy, eventually evaporating in a blaze of radiation. Strange, but characteristic of black holes. To unravel this, let's start with the simplest question. Why do black holes have a temperature? Hot objects radiate. Place your hand near a fire or an oven and you feel the heat without touching it. Place them together and they equilibrate at an intermediate temperature as heat flows from hot to cold. But black holes, we thought, weren't supposed to give out anything. Weren't they introduced as voids in space that consume and swallow everything, dragging all toward a singularity but never emitting anything? After all, the black in black hole refers to this. They absorb light but do not emit it. Yet with the revelation they had entropy, this wasn't quite true. If we could place our hand near a black hole with a temperature of 1000 degrees, the experience should be identical to placing it near a 1000-degree oven. Just as our hand feels photons from the oven striking our skin, transferring energy to skin cells communicated to our brain via nerve impulses, so too must our hand feel photons from the black hole striking the skin and transferring heat. But where would these photons come from? For this to be true, there must be actual particles coming out of the black hole, not just falling in. In the 1970s, this seemed absurd, completely inconsistent with the very idea of a black hole. Could there really be particles coming out of a black hole? Remarkably, yes. Among Stephen Hawking's many contributions to physics, this result is the most important and enduring. The light emerging from a black hole is called Hawking radiation, and it emerges with precisely the spectrum expected for the black hole's temperature. Hawking radiation is theoretically well established and has been derived using many approaches, but all sit at the intersection of gravity, black holes, and quantum mechanics. To understand this, we must consider Heisenberg's uncertainty principle. The idea that in quantum mechanics there is never a perfectly still vacuum, nothing can be completely settled. Imagine yourself close to, but just outside, a black hole's horizon. If you crossed this horizon, you would fall in, your fate sealed. But suppose you have a rocket with enormously powerful engines, strong enough to keep you just outside the horizon. The engines fire constantly, holding you in place. Imagine two beacons on the rocket, one facing the black hole horizon, the other facing away. Light emitted from the horizon side beacon immediately crosses the horizon and falls into the black hole, never to return. Light emitted from the other beacon, pointed away, escapes the black hole and reaches deep space. This is similar to how Hawking radiation works. Contained within Heisenberg's uncertainty principle is the idea that in quantum mechanics, even the emptiest vacuum is not empty. There is an intrinsic energy associated with it. It's even possible to borrow energy from the vacuum for a short time. The more energy borrowed, the shorter the allowed time. This means that for very brief moments, the vacuum can borrow enough energy to temporarily create particle-antiparticle pairs. Provided these pairs rapidly reannihilate, returning the energy to the vacuum, no laws of physics are broken, and energy conservation is upheld. Though strange, this is part of the complexity of the quantum vacuum. Nothing is straightforward. Added to this is the fact that this vacuum isn't just empty space extending in all directions. Here, we're considering space just outside a black hole's horizon, with gravity always ready to pull objects inward. This vacuum has a direction inward. So what happens just outside the horizon when energy is borrowed from the vacuum to create particle-antiparticle pairs? Or for particles like photons that are their own antiparticles, a pair of back-to-back photons. For a tiny instant, energy can be borrowed to create a pair of photons. During that incredibly short instant, these particles can travel, and one of the pair crosses the horizon, the one-way portal to the singularity. The pair can no longer come back together. Just as our rocket teetering on the edge fires photons both into and out of the black hole, so does the quantum vacuum. While one particle escapes to infinity, the other falls into the black hole, and the borrowed vacuum energy must be repaid by the black hole. The net result is that one photon escapes, taking a tiny bit of energy with it, and this energy is repaid by the black hole losing a tiny bit of its mass energy. Detailed calculations confirmed Hawking's intuition that this process resembles a hot oven radiating light. The spectrum of photons emitted by the black hole exactly matches that of a hot oven with a temperature given by Hawking's formula. So there it was. Stephen Hawking found that black holes were not black, but that wasn't the end. As ever with black holes, solving one problem introduced another, because if you wait long enough, the black hole would eventually evaporate entirely. There would be no interior left. Imagine a history starting before the black hole forms, with countless encyclopedias and databases falling in under gravity to create it. Over time, the black hole evaporates, and at the end, there's a gas of particles radiating from where the black hole once was. So what happened to all the information that was once there? According to Hawking's calculation, the emitted radiation was a perfectly featureless thermal spectrum containing no trace of the original information. Where did it all go? Could the information be reconstructed from the emitted radiation? For 2 decades, this question was debated. In ordinary quantum mechanics, information is not lost. Were black holes like this? Or did the unusual combination of gravity and quantum mechanics lead to fundamental differences? Eventually, the answer came from an unexpected direction. The fact that entropy was proportional to the area, not the volume, of the black hole. This was the first sign of a deep and subtle idea called the Holographic Principle, with huge consequences for our understanding of the universe. Imagine dropping a book into a black hole. How you do this, somehow withstanding the brutal accretion disk and radiation waves, is unimportant. The key is you do. We can imagine the book falling until it reaches the central singularity at the black hole's heart, where any information it carries is utterly crushed. To understand whether information is destroyed or survives, we'd need to understand this central singularity. What is the interior of a black hole like? Does information survive in a theory of quantum gravity? If we recorded every photon emitted via Hawking radiation, could we, in principle, reconstruct the information? Most ideas discussed so far, the existence and entropy of black holes, Hawking radiation, were largely worked out by the end of the 1970s. But over the following years, physicists realized black hole physics held even deeper, stranger truths. In particular, it gave the first hints of one of the most remarkable and shocking properties of gravity: the holographic principle. This principle offers the best framework for thinking about information lost to a black hole. To begin, let's return to Hawking's formula for black hole entropy. There's a part that may not seem unusual but is actually groundbreaking. The entropy of a black hole grows with its area, not its volume. Physicists knew that a black hole's mass relates to the area of its event horizon, the spherical shell inside which nothing can escape. For the simplest Schwarzschild black hole, this horizon area depends simply on mass. For spinning black holes, the expression is more complex, depending on both mass and spin. But by 1971, Stephen Hawking showed that whatever happened to a black hole, even including processes that extract angular momentum and slow its spin, the horizon area would only increase. In the second law of thermodynamics, it is entropy that can only increase. First Einstein, then Hawking realized that it was the horizon area, not mass, volume, or angular momentum, that behaved exactly as entropy should. When objects fall into a black hole, adding information and entropy, the horizon area increases. When two black holes merge, the product's horizon area is larger than either component. In complicated slingshots that extract mass and angular momentum from a black hole, the mass decreases, but the horizon area increases. Why is this surprising? Black holes, as we've seen, are similar to gases in some ways. Both are thermodynamic objects with temperatures and entropies. Like hot gases, hot black holes radiate. However, there's an important and subtle difference. The entropy of any object measures the total number of internal configurations it can have, the number of ways to rearrange its innards while keeping external properties the same. For a gas, entropy grows with volume. Imagine a balloon at constant pressure. The larger the volume, the more possible internal configurations of the gas. Suppose we divide the gas volume into many little blocks, each a unit volume of space. Each block can be either on or off. Perhaps on means a gas particle is present, off means it's not. This is a simplified way to think about a gas, but it helps understand entropy. How many total configurations are there? Each block has two choices. With one block, two choices. With two blocks, 2 times 2 equals 4. With 3 blocks, 2 times 2 times 2 equals 8. For 100 blocks, we multiply 2 by itself 100 times. In general, the number of configurations is 2 raised to the power of the number of blocks. So what's different about black holes? For black holes, the Bekenstein-Hawking entropy depends on the area of the horizon, not the volume. The counting looks similar to gases, but only if we do it on the horizon, not the interior volume. Thus, the holographic principle states that for many gravitational systems, the physics is entirely encoded on the boundary of the system. The equations for gravity in the interior can be rewritten or translated into a different set of equations describing a non-gravitational theory that lives only on this boundary. Gravitational systems in three-dimensional space can be equivalent to non-gravitational systems on a two-dimensional boundary. Gravitational systems in five-dimensional space can be equivalent to non-gravitational systems on a four-dimensional boundary. Gravitational systems in a certain number of dimensions are equivalent to those in one less dimension. One dimension in the gravitational theory turns out to be redundant. This idea, also called the ADS/CFT correspondence today, is one of the deepest in modern theoretical physics, supported by vast calculations. The key claim is that two separate mathematical theories, a gravitational theory in, say, 5 dimensions and a non-gravitational quantum theory in 4 dimensions, are actually identical theories, just written in different languages. This has been proposed as a way to link the previously incompatible gravity and quantum mechanics, the holy grail of modern physics. The Bekenstein-Hawking entropy formula was the first inkling of this theory. But how does holography help with the information paradox? Where has all the information gone? Holography tells us that a gravitational system and its evolution can be described through an alternative, non-gravitational language. Suppose a gravitational system with a holographic description has a black hole that forms and evaporates. In the gravitational theory, we'd worry about information loss. But in the alternative holographic lower-dimensional description, the formation and evaporation occur in a completely non-gravitational language. Here, it's simply an ordinary quantum mechanical system evolving ordinarily, with no problems involving singularities or horizons. In such a system, there's no question of information loss. The information is kept on the horizon, stored on a lower dimensional boundary. But even if we know information is preserved, where is it exactly? The best answer so far is that it lies in the details of Hawking radiation. Although we might think of the radiation as emitted like from an oven, all uncorrelated, this isn't quite correct. Instead, physicists believe all emitted photons are subtly correlated and entangled with each other. And it's here that the details of the information that fell into the black hole reside. So black holes are truly bizarre objects that challenge our notions of information and reality. But what are they made of? Once formed and before they evaporate, can we say what a black hole actually is? For a gas, the microscopic configuration involves the locations and speeds of all its atoms. What's the analog for black holes? This question isn't easy and seems impossible to test experimentally. To access a black hole's interior and see what it's made of, a hypothetical rocket with future technology must first cross the horizon. But once it does, it can never leave, so whatever knowledge it gains can never be sent back to scientists outside. So the interiors of real black holes, many light years distant, hidden by the horizon, are beyond our reach both practically and in principle. But mathematics can reach where rockets cannot. If we can't do experiments, the next best thing is thought experiments or mathematical calculations of ideal systems that share key properties with the real world. By understanding such tractable systems, we hope to gain insight into real-world systems. Are there mathematical examples capturing some physics of real black holes but with enough symmetry to allow calculation? In some cases, yes. In a famous 1995 calculation, Andrew Strominger and Kumran Vafa of Harvard University studied a highly stylized example of five-dimensional black holes in string theory. These black holes are mathematical, existing in a world with one extra spatial dimension. They were also very specific, with extra symmetries and properties not found in ordinary black holes. But for these special black holes, Strominger and Vafa were able to count and determine precisely the possible inner microstates corresponding to a black hole solution, all the inner stuff making up the black hole. In this example, the answer involved extended string theory objects called branes. Counting all the ways these could be combined, they obtained an answer that precisely agreed with Hawking's calculation. Though only for a mathematical universe with extra dimensions and symmetries, this was still a significant result. In this simplified situation, they could understand the entropy formula for a black hole from a microscopic perspective and count all the states making up the black hole. Unfortunately, for real-world black holes like Cygnus X-1 or TUN 618, we still don't know what their internal microstates are, or how their interiors are precisely captured by physics on their horizon. But ideas like the holographic principle give hope that one day we might glimpse inside. Perhaps not until further surprises emerge from these mysterious objects at the intersection of gravity, astrophysics, and quantum mechanics. So, almost 300 years after they were first proposed, nothing in the universe remains as mysterious as a black hole. If you found this exploration of black holes fascinating, make sure to subscribe for more deep dives into the cosmos. Hit the like button if you enjoyed the journey, and share this video with fellow space enthusiasts to keep the conversation going. Perspective, and count all the states making up the black hole. Unfortunately, for real-world black holes like Cygnus X-1 or TUN 618, we still don't know what their internal microstates are, or how their interiors are precisely captured by physics on their horizon. But ideas like the holographic principle give hope that one day we might glimpse inside. Perhaps not until further surprises emerge from these mysterious objects at the intersection of gravity, astrophysics, and quantum mechanics. So, almost 300 years after they were first proposed, nothing in the universe remains as mysterious as a black hole. If you found this exploration of black holes fascinating, make sure to subscribe for more deep dives into the cosmos. Hit the like button if you enjoyed the journey, and share this video with fellow space enthusiasts to keep the conversation going.